In this lecture, we will discuss about projective image transformation, which is the most general form of geometric image transformations. Projective image transformation is basically a combination of affine transformation. This is affine transformation plus projective warps. So this is projective image transformation. Some properties of projective image transformation are: unlike affine transformation where parallel lines remain parallel, in this particular case, parallel lines may not necessarily remain parallel and they may intersect at some point. Invariant properties are that straight lines remain straight, and that is collinearity is preserved. Another important property of projective transformation is that two images of same 3D world point taken at different camera angles are related by projective transformation. We can formally define a planar projective transformation as a linear transformation on homogeneous vectors represented by a non-singular matrix. Here, this x, y, h vector and x prime, y prime, h prime vector are homogeneous representation of points in image before and after projective transformation. And this H is the homography matrix. The projective transformation matrix is also called as homography matrix. So, since these 2 points are the homogeneous representation of points, therefore without loss of generality, H and H prime can be written as 1, because there are nothing but the scaling factor. Here this H is also homogeneous matrix, that is since it as in homogeneous representation of point, only the ratio of matrix elements is significant. So ratio of this matrix elements are significant. Therefore, without loss of generality, this can also be taken as, this H33 can also be taken as 1. And it follows that projective image transformation has 8 degrees of freedom. That means to obtain this homography matrix, we need to compute these 8 parameters. Now, how to compute this homography matrix? So, the projective transformation or the homography matrix can be written in inhomogeneous form as this. It is nothing but this is x prime plus by 1, because if I need to write this as inhomogeneous coordinate, I will write it like this: y prime by h prime. Since h is 1, so it can be written as and here also I can multiply this x h11 y h12 and 1 H13. So I will divide this first by 3 to get values of x and 2 by 3 to get values of y. So in homogeneous form, this homography matrix can be written like this. Now, since each point correspondence give two linearly independent equation in 8 variable, we need at least 4 corresponding points to evaluate H. That's why suppose these are my two images. This is the image. If I apply projective transformation, I get this image. So to compute this matrix H, I need at least 4 pairs of corresponding points in both the images. Why we need 4 pairs of corresponding points? Because from one point I am getting 2 linearly independent equations. So from 4 pairs of corresponding points I will get 4 linearly independent equations. So I have 8 linearly independent equations and 8 unknowns. So it can be easily solved. Now let's understand this, how to estimate this homography with an example. Suppose one pair of corresponding point is 2, 4, 1 and 5, 5, 9, 1. Suppose this is 2, 4, 1 and this is 5, 9 and 1 in homogeneous representation. This is x, y and this is just 1. X, y and this is just 1. So suppose I am taking this one pair of corresponding points. I have total 4. So if I take this one pair of corresponding point, this x 2 by 1 is equals to 5h11 plus 9h12 plus h13 by 5h31 plus 9h32 plus 1, which I can further solve and I'll get h10h31 plus 18h32 plus 2 is equals to 5h11 plus 9h12 plus h13, or I can write it as h32 plus 4 is equals to h21 plus 9h22 plus h23. So from one pair of corresponding points I get these two linearly independent equation. Now I can, for 4 pair of points I'll get total 8 equations, and I'm writing these equations like this: 5, 9, 1. This is h11, h12, h13. Then for this equation I don't have any h21, 22 and 23. So I leave those things blank. So these are 0. Then again this is minus, if I take that to other side, it will be minus 10 for h31, minus 18 for h32 and minus 2 for H33, because H33 is 1. So it will be minus 10, minus 18, minus 2. Similarly, for y equation, I'll get minus 20, minus 36, minus 4. Similarly, I will have these for other 3 pairs also. So total I'll get 8 equations. This is H11, H12, H13, H21, H22, H23, H31, H32, H33. So I can write it in this manner. These are the coefficient with respect to this. So in matrix format, I can write it like this. Now I have these knowns here and I have to estimate this H vector. So this equation, I can write this as a matrix H, and now this equation can be solved by computing SVD of A, that is A is equals to USV transpose. So for any given matrix AMN, here I have M and N both 8, but suppose instead of 4 pair of corresponding, these 4 pairs are minimum requirement, is the minimum requirement. I can have more pair of corresponding points as well. So if I have more pair of corresponding points, number of rows will be more. Here since I have 4 pair of corresponding points, so it's a square matrix where M is equals to N is equals to 8. So this is the general formulation where I can write it like this. This is M cross M matrix and this is M cross N matrix, and V is equals to N cross N. Now here U is an M cross M orthogonal matrix. Its columns are the eigenvectors of A. S is M cross N matrix with non-negative entries termed as singular values. Here diagonal entries are eigen values of A. Now this V is an N cross N orthogonal matrix, and H vector which we want to determine is the last column of V. So using SVD I can solve this equation and obtain this H vector. And with H, when I get all these parameters, I'll get the homography matrix. So this is the way in which we can compute the homography matrix. And this projective transformation can be used in many applications, like it can be used for removing projective varves. Like if I take this example, in this example, this perspective, in this perspective image, projective distortions are there. That means this is not a perfect rectangular. In original, this is a perfect rectangular door. But when I take an image, due to some perspective projective distortions, this rectangular has been, this shape has been deformed. So if I need to remove this perspective distortion so that I can get perfect rectangular, I can compute H and get this corrected image. This can also be used for stitching two images, and it also used for registering two images, aligning two images, and there are so many other applications of projective transformation. This is all for today's class. See you in the next class.